rather great variety of strange objects. A lambda, a proton, and a K plus, for instance. Which are, these lambda and K plus are names for peculiar particles. Now, from this one, you know you put two baryons in, you see one come out, so possibly one or the other is one. But if you'll study the lambda later, you'll discover that it very slowly, this is easy for it, easy, this is hard for it to do, it disintegrates into a proton and a pi, and ultimately the pi disintegrates into electrons and whatnot. But what you've got here is the baryon coming out again. So we think that the lambda has a baryon number, but the K does not, has 0. And so in counting these other numbers, we have a similar situation with baryons. So we have charge, and then we have baryon number, with a special rule that the baryon number is the number of protons, plus the number of neutrons, plus the number of lambdas, minus the number of antiprotons, minus the number of antineutrons, and so on. It's just a counting proposition. It's conserved. It comes in units. And nobody knows, but everybody wants to think, by analogy, that it's the source of the field. We are trying to guess at the laws of nuclear interaction, and the reason we make these kind of tables is this is one of the trick ways of guessing at nature. If this is the source of a field and this does the same thing, it ought to be the source of a field too. Too bad so far it doesn't seem to be, or for sure isn't anyway. We don't know. Sometimes people think it is, sometimes not. We don't know enough to be sure about that question. Now it turns out that there's a very peculiar thing. I would like to mention, or there are one or two more of these counting propositions called lepton numbers and so on, but you learn nothing new, the same idea. Just counting. There is one, however, which is slightly different, is that there are, in nature, characteristic rates, apparently, with these strange particles. There are rates of reactions which are very fast and very easy reactions to do, and others that are very slow. I don't mean easy and hard in a technical sense. It's a little, actually doing the experiment. It's got to do with the rates at which these reactions occur when the particles are present. Anyway, there's a clear distinction between this kind of a reaction and this. And it turns out that if you take only faster, easy reaction, that there's one more counting law in which the lambda gets a -1 and the K plus gets a +1, and it's called the strangeness number, or hyperon charge, rather. And the proton gets 0. And in that particular rule is right for every easy reaction, but it's wrong for the slow reaction. And then we have a conservation law called the conservation of strangeness, or the conservation of hyperon number, which is nearly right, which is very peculiar. So it's why the stuff has been called strangeness, the number. It's nearly true, and nearly true. But in trying to understand the strong interactions which are involved in nuclear forces, since as far as the strong